So good afternoon. My name is Kuno Son, is Associate Professor at Geomatics Engineering Program in La Salle School of Engineering, York University. And it is my great pleasure to welcome you here today. And on behalf of Geomatics Engineering Programs at York University. So we're very delighted to have you participated and share in our 9th GeoTalks virtual seminar series. And thank you for joining this meeting today. So before I'm going to introduce Andrew Zitt and our guest speaker for this event, I'm going to briefly introduce our program to the audience. Geomatic Engineering program at York University was founded 20 years ago. We're going to have a 20th birthday this year. So for 20 years in the past, many graduate students, undergraduate, graduate students has been graduated through our programs who are now leaders in various fields of geomatics areas as engineers, scientists, entrepreneurs, and educators. So our program has also primarily contributed to geomatic research communities and industries by conducting innovative research projects. So GeoTalks is a bi-weekly seminar series and organized by Geomatics Engineering Program at York and together with the Canadian Institute of Geomatics Toronto branch. This series will host industry leaders, entrepreneurs in geomatics, and this is opportunity to hear from industry leaders and who will introduce their cutting-edge geospatial technology through this seminar series. Today, we honor to have Andrew Zitt and who joined the Teledyne Optech in 2013. Since joining, and he has gained a holistic view of laser scanning through multiple roles and from customer support and field work to system engineering and product design. In 2019, and he took on the role of product manager software, and where he is focused on delivering innovative software solutions to clients' challenges. Andrew has a bachelor degree of mathematics in mathematical physics from the University of Waterloo and brings a strong technical background, hands-on approach, and custom-focused attitude to all the work he does. Today, he's going to give a presentation to us under the title of Fundamentals of Lidar Technology and Latest Advancements. So Andrew, now you can.
Thank you very much, Kunio. I'll just share my screen here.
Good.
Okay, can you just confirm you're seeing the presentation there?
Very well, right.
Great. Terrific. So thank you very much for the kind introduction, Kunio, and it's my pleasure to join you here for this webinar series, and thank you to all the attendees for taking time out of your valuable Wednesdays to sit with us here. So as Kunio said, my name is Andrew Zitt. I'm the product manager for Lidar software at Teledyne Optech. For those that don't know, Optech, as it was once called, is a company that was founded in 1974 by a York University prof. So that was Dr. Alan Carswell. So I know he has, at least 1 or 2 scholarships at the university in his name, and we as a company are thrilled to continue sort of that tight relationship. He's long since retired, or at least several years retired, but we're very happy to continue collaborating with Gunyo's lab in particular and YorkU in general. So today I'm going to be talking, if the slide will advance, there we go. Today, as Gunyo said, I'm going to be talking about sort of fundamentals of LiDAR. We'll go from the very basics of, what is a LiDAR all the way to, some of the more, the stuff I find more interesting in the latest advancements of LiDAR technology. So as I said, we'll get into, how does the LiDAR system work? What can affect your LiDAR data, why you might use LiDAR over other remote sensing technologies, and a little bit about, what kinds of LiDARs are out there. And then we'll get into the fun stuff. So hopefully there'll be, something here for people who don't know anything about LiDAR, don't even know what this word LiDAR means, and all the way up to, hopefully there will be something new for those of you that are familiar with it. So I'll start from the basics. LiDAR is actually an acronym, so it stands for Light Detection and Ranging. More commonly known acronyms are sonar and radar, right? Which are essentially the same thing. So sonar is sound navigation and ranging. So you're sending a ping of sound energy and waiting for that ping to reflect off something and come back to you. Radar is very similar, but you're using radio waves. And LiDAR is the same as well, but we're using light or in this case, lasers. So, at its most basic form, basically the way a LiDAR system works is we shoot a laser at something. We measure the time that we shot the laser. So we call that T0 usually. And we wait for that light to come back to us. And then we measure the time that we see the light come back. So that's what we call TR, or the time of return. And that's T0 plus some time N. So, subtracting the time we fired the laser from the time we got it back gives us that time, and we multiply that time by the speed of light, because of course lasers travel at the speed of light, and that gives us a distance, right? And more precisely, it actually gives us a distance to the target and back. So we divide that by 2, and that's how we get our range measurement. So hopefully that's pretty simple, the sort of the bare bones basics of it. And I just wanted to sort of pause here to say that, LiDAR systems, they're getting cheaper, but they sort of typically range in the tens or hundreds of thousands of dollars. So you may not sort of think of it as something that's accessible to you, but these are all some examples of where LiDAR might be seen in your everyday life, or closer to your everyday life. So, these range finders that golfers use or hunters use, or even these sort of laser tape measures, used in construction and renovation, they're all essentially LiDARs. They're not scanning LiDARs. They're just, a single beam going in one direction, but they're effectively LiDARs as well. Sorry, my next slide button is a little sticky here. So as I said, these, what's justifying that $10,000 or $100,000 price difference? Really a modern LiDAR system, when we talk about LiDAR, is much more than just a laser rangefinder. So first of all, we're going to scan the beam, often, in one direction, sometimes in 2 directions. And, a range measurement gives you 1 dimension, right? But we're interested in measuring things in 3 dimensions. So scanning that beam across 1 angle gives you a 2nd dimension. Now you're talking about, 1 angle and 1 range. And so you're doing 2D data at that point. And then either scanning the laser in a 2nd direction or moving the system can give you that 3rd direction. So, we do have systems that scan in 2 different angles and give us those 3-dimensional data directly. But most of Optech systems are actually, what are often called kinematic LiDAR sensors, in that, they scan in 1 direction, gives us 1 dimension. They measure the range, that gives us a 2nd dimension, and then they move around, and that gives us our 3rd dimension. So in that case, we're typically using GPS and inertial sensors to tell us where we are, where we're pointing, and then, the laser scanner gives us the other 2 dimensions. And then just a little note here that, more and more LiDAR sensors are being integrated with cameras, or, whether they're RGB or multispectral or, shortwave IR, near infrared, whatever, or even, ground penetrating radars or other kinds of sensors to add, complementary data. So, the LiDAR is really good at mapping 3D stuff that it can see, but maybe you're interested in underneath the ground as well. And so we, strap a ground penetrating radar on there, and now you've got much more rich geospatial data. So just a few examples of the LiDARs that we offer. And these range, as you can see here, from beneath the ground all the way up into space. So this at the bottom here is our cavity monitoring system. So the idea here is you stick this thing basically on a pole and shove it into a cave, and then it scans. This is an example of one that scans in 2 different angles, and then there's a rangefinder out the front head here. So that can give you a nice 3D picture of your cavity. Similarly, the Polaris is also a full 3D LiDAR. So this is our terrestrial LiDAR system that, typically you would mount on a tripod and scan a full 3D scene. And then we've got our mobile sensors, which are, mounted to a car and driven around. Some of our more recent sensors are meant to be mounted on UAVs. So that's these small guys here, the CL line of sensors. And then we've got, what has become sort of the de facto thing that people think about when you say LiDAR most times is airborne LiDAR. So we've got a few different flavors of airborne LiDAR, from, the Galaxy, which is our flagship sensor, mostly for wide area mapping, to the seismil sensor, which is a bathymetric LiDAR. So this one actually uses a green laser to penetrate the water, and you can map the seafloor. And then, something that I find really cool as well is that, we've also sent a bunch of sensors to space. So up on the top left here is an example from the Phoenix lander mission. So Optech and actually York University as well collaborated with the Canadian Space Agency and NASA and a few other industrial partners to make a LiDAR that actually pointed up into the sky. So this was to measure the atmosphere on Mars. And, I think it's a sort of nice story to tell that this sensor that we put on the Phoenix lander is actually the first thing that was ever used to detect snow on Mars. So it's sort of a nice Canadian story to say that, a Canadian company found the first snow on Mars. It's fitting. And then over here on the right, these 2 images are from our latest space mission, which was the OSIRIS-REx mission. So you may have seen some news or some articles in the news a few months ago, where this is essentially a mission where NASA wanted to send a spaceship out and collect a sample from an asteroid in outer space. So essentially, you can see the 3D data here from that asteroid is coming from our design of the LiDAR here. And again, that was actually in collaboration with York University. So it was a professor named Michael Daly, who was the principal investigator on that project. Next year. So, when we're talking about LiDAR, this is where it'll start to get hopefully a little more interesting for those that are familiar with LiDAR is, oftentimes these things are bought based on a spec sheet. And one of the things that everyone looks at on their spec sheets is, how far can I shoot with my LiDAR, right? How far can I shoot this laser and expect to get a 3D point back? So what are the things that go into that? So one of them is the wavelength of laser. So, I sort of mentioned earlier that green lasers are good for penetrating water. For airborne applications, we're more interested in penetrating the air column and avoiding solar background radiation. So you're trying to find this balance of what wavelength of light can get to my target and back as efficiently as possible, and not pick up so much background from the sun, or not pick up sort of other sources of light radiation that can trigger the receiver. Another one is pulse width. So this is essentially how short in time can I turn my laser on and off. So this is important because most of the lasers we use are what we call average power limited. So what that means is that, when the laser manufacturer says, okay, this is a 1 watt laser, and you're putting out little tiny pulses, the shorter you can get that pulse, the higher amplitude you can get out of that pulse. And that's really what matters when it comes to shooting further and further. So squeezing those pulse widths as short as possible is really important. And it also helps with some other aspects of the LiDAR, which hopefully we'll have time to talk about later. Sensitivity of the detector is really kind of a, sort of an obvious one. It's a little bit boring in my mind. You kind of just, again, pick the one that works the best at the wavelength and avoids all the solar stuff. And then this one is the one that's maybe sort of the most surprising. So it's the area of the receiver aperture. So that's how big is your window or your lens, essentially. So we're going to talk about that over the next few slides here. So again, just a very sort of cartoon example, but hopefully this will illuminate some intricacies of why the area of the receiver matters so much. So essentially, as in the previous diagrams, we're going to shoot this pulse of light out of my target, right? And by the time that pulse of light gets to my target, yeah, it's grown, but essentially all the energy is still in this nice little packet. Now, the thing that a lot of people don't realize about LiDARs is that once this packet of energy hits the target, most targets, whether it's soil or asphalt or a painted wall, most of them are what we call diffuse reflectors. So what that means is essentially the light that hit the target is not going to come back in a nice tight packet anymore. It's going to get reflected in all directions, essentially. And sorry, the slides are. And so what that means for us as LiDAR manufacturers is, instead of getting that nice tight packet of energy, you've got this dome of energy coming back. And by the time it actually gets back to the sensor, that same amount of energy is now spread out over a huge area, right? And really, if this green box sort of represents the size of my mirror or my lens, that's all the energy I can get back, right? Or that we can get back. So, having a bigger aperture or opening for the light to come back to is really critical to collecting more of that energy. And of course, then the challenge becomes, if you're, you can always sort of put a bigger lens on a camera. That's not such a big problem. But with a LiDAR, you're scanning this beam around often quite quickly. And so that means your mirror has to be that big. That means all the optics inside the sensor also have to be that big. And when you're trying to move these big parts, that becomes a real challenge. So that's in large part why it's not a trivial problem to just pack more light into my laser and make it shoot further. So to sort of put some numbers to this, I promise this is the only equation in the presentation here, and I'm not going to go into tremendous detail about it. But this is a well-known equation. If you Google LiDAR equation, this will almost definitely come up, or some flavor of this. And essentially this is showing, what is the signal level based on all these parameters. So, as we talked about, the laser pulse's peak power is very important, and that's a function of the average power and the pulse width and the frequency that we're shooting the laser. And then, the size of the aperture, as we also talked about. Choosing the right receiver is also very important. And then, you start to get into sort of all the physics stuff. So, how efficient are your optics and your electronics? How reflective was the object to begin with, right? So if you've got a nice bright white target, that's going to reflect a lot more light at most wavelengths than, say, for example, a piece of asphalt, especially a wet piece of asphalt, is particularly bad at the wavelengths that we tend to use. And then there's also, this atmospheric coefficient, which is basically how much energy is the atmosphere absorbing, right? So we all know that the atmosphere is not empty, it's not a vacuum. So those air particles are fighting against us as well. So next is a little bit, I talked about how a LiDAR works, and that was sort of one type of LiDAR. So that's what we call a time of flight LiDAR, and that's, what Optech is known for, and I think all of our sensors are time of flight sensors. But there's also, a different technology for measuring range from lasers, and that's phase shift. So essentially the way that works is you send out a continuous beam of light. So instead of those short pulses, you're just shining the light constantly, but you're varying the amplitude of that light. So you're modulating the amplitude. And then when you receive it back, you're measuring the phase difference between, your outgoing pulse and your incoming pulse. And that lets you measure a range as well. So I'm not going to talk a whole lot about that, but it's worth mentioning that that's sort of an alternative approach to measuring distance with lasers. Another interesting thing about LiDAR is that we get an intensity value. So that intensity value is basically a measurement of the amplitude of the returning signal. So as I mentioned, asphalt is a lot less reflective than, say grass in this example would be good. And so you're going to get a darker or a less strong signal back. So if you're just measuring ranges and mapping things in 3D, you get an image like this. And there's valuable information here, certainly. But adding that intensity gives you another dimension, right? So now I can actually see where the lane markings are on this road, or I can see that this is a parking lot, and whereas without that intensity image, maybe that just looks like a field to me. So intensity is another valuable thing that LiDAR can provide. Another nice thing about LiDARs is that we can record the full waveform. So usually, most of Optech systems basically measure discrete returns. So, we shoot the laser and we wait for it to come back and we measure the time, and it's almost like a stopwatch. But there's also this idea that, we can also record the entire signal that comes back. So that's often termed waveform recording or a digitizer. And that can be really useful in some applications. It can be even necessary in some applications. But it does generate a whole lot more data. So it's sort of one of those things where, if you don't need it, you probably don't want it. But if you need it, it's priceless. So some of those things that you might need one for are returns that are merged with other returns. So, we'll talk a little bit about this later in more detail. But essentially, if you have sort of 3 targets that are all reflecting light at you, you'll probably get a pulse that looks something like one big pulse, but in fact, you can split that up into 3 separate distinct targets. And that's done with, you know, all sorts of fancy applied math and signal analytics to be able to say, you know, this is 3 returns, not just one big wide one. The other area where waveforms become really important is for bathymetric LiDAR. So here's an example of that where, you know, the water surface, when the laser hits the water surface, then we start to get a rise in signal. And really the water column itself will have this sort of solid red profile. And then we'll get, you know, a particularly high signal when we hit the surface because there's waves and air bubbles and things like that coming up to the surface. And then we'll also get a, you know, this second pulse from the bottom, from the seafloor or the lake bed. And really without the waveform digitization, you know, it's a lot more difficult to, I won't say impossible, but it is a lot more difficult to create a bathymetric LiDAR. So what can affect my LiDAR data? Again, I've got more lovely cartoons for you. So the angle of incidence is sort of a big one. So what I mean by angle of incidence is, you know, is the target flat or normal to the sensor or to the laser, or is it sort of slanted like this? And the reason that can have an effect is, you know, and as we talked about, this isn't exactly an accurate diagram because the returning light isn't going to come back in a sort of trapezoid shape like this. But the fundamental point is that, you know, this bottom corner of the laser pulse is going to hit the target first, and then it's going to start traveling back. And then sometime shortly later, this top corner is going to hit the target, and then it's going to start traveling back. So you do get this sort of stretching of the signal. And as a result, you would, you know, if the target is flat and you get sort of this blue curve, we would actually see this sort of red curve from a slanted object. So that's another area where the waveform digitizer can help because, you know, we've got ways with our, call them discrete LiDARs, to figure this out and assign the right range. But knowing that it's also stretched can give you information about the orientation of the target or the properties of the target. Another one is surface reflectivity. So we talked about that, you know, if it's dark or wet, you know, a lot of these sensors are using infrared lasers. So water is not the friend of infrared light. It absorbs it quite a bit. So, you know, that can affect your LiDAR data as well. And then the last example here is, you know, if you've got like a mirrored object, what we call a specular reflector, you know, basically all of that energy is going to bounce off that thing, likely not right back at your receiver, and you know, that thing is gone. So we're not going to get a point from that. And then, you know, just a few more things. So day or night doesn't really matter for LiDAR. I mean, in fact, we can sort of get away with a little bit more at nighttime. But we are generating our own light with the laser. So we don't need sunlight. It's not like cameras where you need a you know, sunlight or some other external source of light. We're generating our own signal. So day or night doesn't matter. Dust, vapor, precipitation, that does matter, right? We're shooting these lasers through the air. If there's stuff in the air, that's going to sort of impede our laser energy. Background noise is, I mean, fundamentally it is an issue, but we design the systems in such that they are, you know, immune or at least resistant to that. And then temperature, you know, fundamentally no, but, you know, there's some sort of, you know, the electronics can be affected, and you know, the density of the air can affect the speed of light. So there's some intricacies there, but for the most part, you know, these things can operate in winter, summer, whenever. This one I'm not going to spend a whole lot of time on, but when we start to look at it at the system level, there are all sorts of other things that can mess up our data, frankly. So there's the quality of the laser and Lidar sensor itself. Then if we're talking about a kinematic solution, there's all the stuff that goes into knowing where we are and where we're pointing. There's all sorts of calibration concerns. Are your control points okay? Like, oftentimes the people that are using these LiDAR sensors are wanting to validate them with some independent control points. And, we need to be careful that those are done correctly in the right reference system, all that good stuff. And then, there's obviously sort of the operational stuff. So, are you following the best practices? Is there some user error involved? And then there's the software, which is an increasingly important part of this whole ecosystem where, traditionally people were okay to, wait for 3 weeks to get their LiDAR data back from the sensor, from really the software that was processing the data. But that's really starting to change in a big way. So there's, cases where you might still be able to get away with a couple weeks lead time, all the way up to, cases like autonomous driving where, if it takes 2 weeks for you to decide that there's a pedestrian in your way, that pedestrian isn't doing so well anymore. So, so all the way from, still accepting, some delay in the processing all the way out to real-time requirements, the software is really a critical piece of that. So moving on to sort of, why would you choose LiDAR as your remote sensing technology of choice? And, there's a variety of reasons, right? And it's not going to be the right technology for all applications, but, there are certain applications where LiDAR is, if not the only solution, it's definitely the best solution. So what are those? I guess some advantages of LiDAR over, say, sort of traditional metrology is that it's non-contact, right? You're not touching anything. So if you're trying to measure something up in a ceiling or in some dangerous area, you can send the sensor in or stand back and scan the sensor over it and not have to worry about putting people in harm's way. So, a good example of that is for road work, right? Would you rather stand on the side of a highway with a GPS RTK rod and sort of have to close down the road or all that sort of headache? Or would you rather sort of drive down the road in your mobile mapping vehicle and just scan it and measure it in more detail than you would get from the GPS rod in the first place? Another advantage is that it's fast, right? So instead of standing on the road and taking one measurement at a time, we're driving down the road at highway speed or flying over the road at greater than highway speed, flying speed, and getting even more detail. And really, I think the crux of this slide is, versus photogrammetry, right? Because, photogrammetry has most of those advantages as well. But what photos don't have is the ability to get multiple returns. Well, I guess there's no equivalent to pulse for photogrammetry, but, if you did photogrammetry over a forest, you basically only get the canopy, right? Whereas with LiDAR, you would shine the light down on this tree, maybe part of the laser beam hits some leaves, maybe, another part of it sneaks through and hits a branch, and then some part of it, sneaks through all the stuff above and actually hits the ground. So if you're interested in mapping the forest floor, or getting a terrain map under forestry, LiDAR is really, your only practical option. Another advantage we talked about already was day or night operation. And then the other one is direct measurement. So again, comparing with photogrammetry, photogrammetry, I guess for those who don't know, is essentially the idea is you take a photo from here, you take a photo from over there, and you find some common object and you do some triangulation, some trig calculations to figure out where that point is in 3D. Whereas with LiDAR, we're measuring that directly, right? So there is an inherent step that we are skipping relative to photogrammetry. And, so that's sort of the advantage that you see in real-time applications like autonomous driving, where, we're getting the full 3D scene with pretty high fidelity, pretty much out of the box. Whereas with photogrammetry, if you're taking a picture of, say, a cornfield, how do you tell this corn stalk from that corn stalk in order to be able to match them and do your triangulation? It's not a trivial problem at all. So those are some of the reasons why you might use LiDAR. And here's just a nice example of that multiple return capability. So on the left, you see, the tops of the trees and sort of probably some of the middles of the trees. This is basically the full LiDAR data set. And then, you can remove all that stuff and just look at the ground and get your terrain model for doing, water runoff analysis or flood mapping or whatever the case may be. So getting into the sort of technology bits, what kind of LiDARs are out there? So I'll start with sort of what Optech's bread and butter is, and that's oscillating scanners. So the idea here is, you shoot your laser beam at a mirror, and that mirror sort of oscillates back and forth. And the result is, the laser beam sort of sweeps across in both directions and maps the terrain underneath you. So, the advantage to this is that you can change the field of view, right? So you can tell the scanner, I only care about 10 degrees, so focus all of my laser points there. And then you can just plaster that small area with laser shots and get really high resolution data. I guess some disadvantages about that is that, you get this sort of back and forth scan pattern, which, is fundamentally fine, but, it's not sort of as visually pleasing to the eye. They are definitely harder to manufacture and calibrate. I can speak to that from experience, but we've pretty much figured that out. And that's part of our sort of secret sauce here. And then another disadvantage is that it's one of those 2D LiDARs that I described. So, we are really only scanning in one direction, getting a range, so that's 2 dimensions. And then the third dimension we're getting from the motion of our platform. Another very common style of LiDAR or mechanism to scan a laser beam is with a rotating polygon. So this is a pretty simple example. This one I think is actually from a barcode scanner, but it's basically the same principle, and it's a multifaceted mirror. So you've got this polygonal shape with mirrors on all sides, and you're shooting your laser beam at that mirror, and as it turns, you're gonna pick up the next side when it's available. So, an advantage to that is it's a lot easier to manufacture, right? Like, spinning something in one direction just is a lot easier than sort of trying to swing it back and forth. So just dynamically and mechanically, it's much, much simpler. You also get that nice gridded point spacing. So, because you're only scanning in one direction, you don't get those sharp points at the edges. But you're limited to a fixed field of view. So, what that means is it essentially operates much like a camera. And if we sort of switch back to our slide for the oscillating scanner, this is what you would get from a fixed field of view when you fly over a mountain, right? Because as the mountain comes up at you, your field of view is constant. So as the range gets shorter, your swath gets narrower. Whereas with an oscillating scanner, we're able to dynamically change that field of view and keep those swaths nice and evenly spaced. And that's really important for maintaining efficiency, right? You don't want to be sort of filling in gaps after the fact. You want to just plan your flight and execute it in as few flight lines as possible. Another sort of disadvantage of the polygon scanners is that you lose a lot of data. So, you know, the obvious one is when the laser hits this corner, it's going to sort of scatter in a few different directions and not be very usable. But the other sort of thing that maybe people don't realize is it's not just when the laser hits this scanner, because as I sort of mentioned before, the area of the receiver really matters. So you've got this big, wide receiver telescope essentially, and that the field of view of that telescope is going to be obstructed more for more of those angles than the laser beam is. So you're losing not only when the laser hits the corner, but anytime this receiver field of view is in the corner. So you know, you are losing, you know, sometimes up to like 30% of your data if you're using this method. So there's definitely trade-offs here. Another fairly common scanning mechanism is to use a rotating prism. So the idea here is, you know, you shine your light through the prism rotates and it deflects the laser by some fixed angle. And then, you know, if you get real creative, you can add a second scanner here, and then, you know, you can sort of deflect the laser in two directions. And then instead of just getting a cone, you get these, you know, crazy rosette patterns that can be quite effective for some applications as well. If, for example, you're staring at one thing for a long time. These ones, again, you know, you can get various scan patterns from a single assembly, which is nice. You've got this big wide lens, so you got that big receiver aperture. But as a consequence of that big wide lens, you know, it's really hard to spin that thing really quickly. So that can be a problem. So again, just to sort of make sure it's clear, you know, with an oscillating scanner, you get this back and forth kind of pattern. With a polygonal scanner, you get this, you know, unidirectional kind of pattern. And then with a prism, you know, most of those prism scanners sort of scan in a cone. So, you know, from an airborne platform, if you're scanning a cone underneath you, you get these circles on the ground, which have advantages as well. This last one here we'll save for the next few slides, but this is an example of an automotive LiDAR, which is a multi-beam LiDAR, so we'll talk about that. The next one, which is still fairly new, is, you know, and you know, there's a few different technologies here, but I'm sort of lumping them into one because sort of conceptually they're very similar. And this is the idea of, I'll lump them all into calling them flash LiDARs. So essentially the idea here is instead of packing your laser beam nice and tight, you're going to shine it more like a flashlight, right? And then instead of a single point detector, you're going to have an array of detectors. So for example, this sensor I think has something like 4,000 little detectors and one big laser, right? So they shoot one big laser, it spreads out over some fairly big area, and for each time they shoot that laser, they get 4,000 points back. Now, sort of, again, clearly, I mean, that sounds like a winner, right? That's extremely efficient. You're getting your 3D data out of the box. But really the crux of this one is that you're getting a very low signal to noise ratio. right? All of that signal that you packed into that big flashlight is now getting split up by 4,000 detectors. So it's, you can get really impressive data with these sensors, but a lot of the times there's a lot of software behind this that's, averaging and sort of interpolating between points. And in the survey and mapping community, that's generally frowned upon to sort of not use directly measured observations. So that's sort of the major downside of these, but they can be very effective in certain cases. And then last is the sort of relatively new family of scanners that were really targeted at the automotive industry. So this LiDAR sensor has, you can see them here. Each one of these little boards basically holds a tiny laser. So this is what we call a laser diode. And it kind of comes out the sensor like this, and then each one of these lasers has a matching receiver. And I mean, I could talk about this design for days. I mean, it's a really elegant way to do it. I think it's extremely efficient. It's 3D inherently. That's how we ended up with sort of this picture like this, right? Each one of these rings that you see is from one of those laser receiver pairs. It works really well for sort of those autonomous applications or robotics applications. Really, the main downfall of it is that it's limited to laser diodes, right? You can't exactly put a big laser in a design like this. You're relying on these chip-mounted, or sorry, I say surface-mounted lasers. So what that means is that the quality of this laser beam is not as nice as the quality of some of the bigger lasers that Optech sensors tend to use. So for example, instead of shooting a nice tight small divergence laser beam, these tend to spread out quite quickly, and trying to keep those pulses short is also quite difficult with these lasers. So now into the fun stuff. I'm sort of running out of time here, so I'll try and go through this relatively quickly. So laser technology, like the technology and the components is really making leaps and bounds. That's largely driven by those autonomous driving requirements. So for example, like I said, imagine trying to fit 16 of these lasers into a single sensor. It's going to be a big sensor and probably too big to put on a Ford Focus or whatever car you want to use as an example. So having these surface mounted lasers is really critical to keep the size, weight, and power down and the cost. And previously sort of laser diodes were sort of the only really tiny laser technology. And now there's, more and more different technologies to get these lasers shrunk down, cheaper, lower power. So VCSEL stands for vertical cavity surface emitting laser, I believe. And so those can be really tiny and produce quite impressive power and optical power and beam quality. Oops, sorry. There's also been a lot of advancement in scanning technology. So, we've got these MEMS mirrors that can swing a laser all sorts of places insanely fast. I guess one of the limitations there is that there aren't really big MEMS mirrors. So if you're trying to scan your receiver telescope as well, that can be a problem. There's also, liquid crystal beam steering is sort of a new technology. I've seen some examples where, you've got a lens and you're sort of vibrating it back and forth to steer the laser beam. So that's a neat new sort of idea. And then, in that realm of sort of those flash LiDAR sensors, they're also starting to come up with CMOS sensors that are specifically designed to measure the time of flight. So actually Teledyne, one of our sister companies at E2V, makes such a sensor, and so that is really sort of more like a 3D camera, or a depth camera, if you will. There's also all sorts of new application spaces. So I mentioned autonomous driving, that's driving down the cost, size, and power. I mean, again, if a traditional LiDAR is in the tens or hundreds of thousands of dollars, you can't exactly put that into a car and expect us to sell it for a reasonable price. So these guys are really targeting the sort of sub $100 LiDAR systems. UAS or UAV is exploding in a big way. And really, I think one of the biggest advantages there is that smaller projects are now more affordable, right? Where previously, if you wanted to do an airborne LiDAR collect of your, relatively small mine, for example, you got to deploy an aircraft, whether it's a helicopter or an airplane, you got to hire pilots, you got to, make sure that sensor's ready for you. There's a whole lot of logistics that drive the cost of that way up. So now, someone with a DJI drone and a little LiDAR sensor can go and do those projects at an affordable price, which is sort of opening up more applications day in, day out. Mobile devices, I mean, I think this is sort of the obvious and relatable one where, we all know Apple in the latest iPhones is putting LiDARs in them. And really, I think this is a nice one where, I'm pretty sure that Apple's main motivation for doing that was to make their camera better. But now you've got all these people sort of designing apps that are using the LiDAR for all this this interesting stuff, like 3D modeling from your iPhone. So that's I think going to be a game changer in the survey and mapping industry, right? If you can sort of just take the thing that you have in your pocket already and go do a decent 3D model of a building, a room, whatever the case may be, that's an important innovation. And then there's the sort of handheld, indoor, underground sector that is really making use of SLAM technology. So SLAM is simultaneous localization and mapping. And the idea there is, instead of relying on your GPS and IMU to tell you where you are, you're using the sensor data itself to create the map and to figure out where you are in the map at the same time. And then sort of more in my world is the data processing technology. So I realize I'm running out of time, so I'll sort of fly through this, but we've got automated system calibration, we've got advancements in data management, often facilitated by the cloud and sort of the explosiveness and accessibility of large server farms and huge computability. Same with machine learning is really leveraging that capability. And then multiple pulses in air. I hope I'll still have time to do that. Before I get to that though, this is a nice example of machine learning helping LiDAR where in the bathymetric LiDAR, we need to know which points came from land versus water. And up top, you can see here, this is an example where someone, a person has gone in and manually tried to decide where the water is. And then below is from our deep learning algorithm. And you can see, it found a whole bunch more water that the human actually missed. And it even found, a little island here that the human also missed. It emphasizes that importance of the software as part of this ecosystem. So this is an example of our automated calibration. So we took an automotive Lidar, relatively cheap one, and with our software, we can go from sort of a thick point cloud to a nice tight point cloud just by tweaking the calibration of that Lidar. Another one is multi-pulse. So again, I'll try and fly through this, but essentially the idea is, we're shooting our Lidar so fast these days that the running joke is that, the speed of light isn't fast enough for us because, we shoot the laser once, it bounces off something and it comes back. But if we shoot the laser fast enough, we're shooting the second shot before the first one came back. So that presented a big issue for a long time for a lot of these LiDAR sensors. We had to figure out a way to continue to increase the frequency in order to meet the needs of our clients while still producing, coherent data. I'll skip through this, but Pulse Track is our technology that solves that problem. Another sort of associated problem is if you shoot the laser at exactly the same time as your previous signal is coming back, basically the sensor will miss that. And again, the Pulse Track technology sort of gets around that problem, and where you would usually or traditionally have a scar through your data in that blind zone, now we have fully continuous data. And then the last example here is for atmospheric return. So again, before this multi-pulse thing was a problem, we would shoot a laser, maybe you get something from the, some air particles in the atmosphere coming back, but that's okay because, the stuff you care about is much further beneath that. But once you start to get into this multi-pulse zone, it's very possible for that atmospheric return to come back very close to your to the one that you care about. So again, this is an area where deep learning has helped us tremendously. So I've got to give credit to Gunyo and the members of his lab for helping us with this. So you can imagine this is sort of the case that I described where the atmospheric returns are coming back and mixing in with the ground returns, and through deep learning we're able to identify which ones are real objects versus which ones are the atmospheric returns, and ultimately remove them from the data so that we get this nice clean terrain model back. So that's it for me today. Thank you very much. And I think we've got some question and answer, maybe a couple minutes at least.
Thank you so much, Andrew. Right.
My pleasure.
Exciting. It's a lot of technology we learned today from you. And so people and audience, and if you have any questions, and please write your questions in a chat box. And I'm going to ask your questions on behalf of you to Andrew, right? Okay. So feel free to write questions. Now, so, okay, I already got questions now. From Rafar and Kesmarek. Can you speak to some of the accuracy of the different LiDAR methodology? So you explained us so many different things. So maybe can you pick it up the representative alternative solutions?
Yeah. So I guess I'll start with what I know the least about, and then sort of transition into what I know more about. So the phase shift technology tends to be a little bit more accurate, but you're really limited to short range. So I think I had that in the text of the slide, but I don't think I mentioned it, verbally. Is that it's very accurate. You get very high resolution as well, but you're limited by range, and you're limited by you're more limited in the environmental aspects of the scene. So those are really well suited for like indoor applications, or maybe construction sites, things like that, where you're sort of within a tight area, and those can be millimeter, even sub-millimeter, I think in some cases, precision. As for the time of flight, we're most of Optech sensors are sort of in the 5 millimeter range for those kinds of applications. Up in the airborne, there's it's a little bit more challenging. Those are sort of in the centimeter range, like, a couple centimeters practically, but I think we spec it a little bit higher because, then you're talking about the GPS accuracy and the IMU accuracy as well. So long story short, you can go from millimeter, or there's also laser triangulation, which can definitely do the sub-millimeter stuff, all the way up to, I think the flash is those sort of wide beam examples are probably sort of the worst in terms of the precision of the sensor itself. But through all the redundancy you're getting, you can sort of squash it down and get a little bit better. But say, from sub-millimeter all the way out to, I guess, meters in some case. Like I know there's a Lidar on a satellite up there. That's probably in the meters or tens of meters. So depending on the application, you've almost definitely got a sensor to suit it.
So the second question is from Arash Raki. So is there a technology that uses LiDAR and photogrammetry at the same time?
Absolutely, yeah. So I think almost all of our systems that we sell these days, we're shipping a camera along with it. And I guess the immediate follow-on question is why, right? If LiDAR is so great, why do you still need the camera? And they're really complementary, right? So, it can be as simple as, my human operator is more familiar with images. We want that RGB color, so that can provide a lot of context and ease of use. But then there's also sort of, in the airborne mapping space, most LiDAR sort of point down, right? And they can see through the canopy. So, that's an advantage over photogrammetry. But then the photos, on the other hand, are much better at mapping like building walls or, things like that. So, the two can be quite complementary. Even if all you're interested in is 3D point clouds, you can have a LiDAR that sees through your trees and gets, your bare earth model, and then an oblique camera setup that's capturing all your building facades and infrastructure. So the two technologies are they do a lot of the same stuff, but they're also quite complementary in their sort of advantages.
Okay, so I have another question from Marianne Jamila. Thank you for so much for your presentation, Andrew. I'm not sure how relevant this is, but how much benefit you can achieve with full waveform digitization as compared to discrete ones?
Yeah, that's a good question. So again, I think it really depends on the application. So, on the downside, if all you're interested in is, say, a bare earth model, the waveform probably isn't doing a lot for you unless your vegetation is really low, and then maybe you're sort of in the in the region where those two pulses are merging together. And really it's probably going to ultimately hurt you if you don't need that data. It is a tremendous amount of data that to be storing and processing if you don't need it. On the other hand, if you're trying to do some spectral analysis, or like I sort of mentioned, bathymetry, then the waveforms are extremely important. So again, depending on what the applications are, and we could follow up and go through them. But it may be a complete waste of time, or it could be, absolutely necessary. It sort of depends.
Right. I think the people may have more questions, but I think we're reaching to the end of the sessions. But I have a quick questions, Andrew. You provide a very comprehensive overview about Lidar technology at the moment, right? And perhaps could you add more comments about the multi-frequency laser? So I don't think you covered it up. And second is, pulse tracking is really interesting and promising aspect, but it also reaching to technical limitation. So what do you think, how are we going to resolve this technology? Perhaps the combining phase modulation together with the discrete, and I'm not sure. So what do you think?
Yeah, so I guess I'll start with the multi-frequency. So Optech designed a sensor, as I know Gunyo knows, but the audience probably doesn't know. We called it the Titan, and that was a multimodal LiDAR. So we had one laser, one beam that was 1550 nanometer, one that was 1064, and another that was 532. So two IR or infrared and one green lasers, and those would scan together. And that's really interesting, because then you can start to look at sort of not quite multispectral, but at least trispectral reflectance, right? So the green light is going to reflect differently off plants than the IR light, and that ratio is going to flip on the water, and it might even flip based on the tree species or things like that. So we had a lot of really interesting sort of case studies with the Titan, mostly from the world of academia. There were a couple of commercial clients that were doing bathymetric or topobathy work with it. But yeah, that's really a really interesting sensor to work with, because as I said, you get that sort of those three bands of intensity along with your 3D data. The pulse track sort of limitations, that one's also interesting. So I mean, one way to sort of push that problem even further into the future is again to use multiple lasers, right? Because if you can distinguish between a few different frequencies, that sort of helps you solve that problem, and each laser doesn't have to shoot quite as fast in order to get the same total laser frequency from multiple lasers. So that's sort of one of the things that's really elegant about those automotive push broom sensors. There's a lot of different ways to solve that problem. Sort of the phase shift one, I've actually sort of thought about that same approach in the past as well. I think there's some challenges with it, because really the fundamental problem starts to manifest itself at longer ranges, and that's where the phase shift approach sort of starts to become less effective. So there's definitely a lot of ways to solve this problem. I'll say that, and I think what we've got with Pulse Track is very innovative, and was the right solution for us. I think I know how some other people are solving that problem, but it's sort of all part of the secret sauce of a LiDAR manufacturer. So I don't know how much more I can say than that.
Thanks, Andrew. And for your closing remarks, could you share us sort of a future aspect of laser? And I know the Teledyne Optech is a leader in the world, sort of high energy, long range laser. On the other hand, a lot of cheap short range laser is now in the market for self-autonomous driving cars and UAV. So what is your perspective? What is your plan at Teledyne Optech, the future of the laser?
Yeah, I mean, I think, you know, the different sort of classes of laser or of LiDARs are not necessarily, you know, Optech's LiDAR are better than the automotive ones or anything like that, right? I think they're different tools for different jobs. So, you know, and the way I see it, you know, yes, you know, these automotive sensors are sort of disrupting the market and changing, you know, they're going order of magnitudes than you know, traditional LiDARs. But really, the way I see it, they're helping to make LiDAR a household name or a household word, right? They're commoditizing the idea of LiDAR. And, you know, to go from those sort of few centimeters of precision down to the, you know, millimeters or sub-millimeter that you know, we talk about in the survey LiDAR space, it's not a trivial thing to do, right? And if they don't need to do it, they probably won't do it. So it's, you know, I really see that as almost free marketing for, you know, a company like us where, you know, they're putting the word LiDAR out there. People are going to have LiDARs in their cars soon enough. Some already do. You know, and people have them in their cell phones, even better, right? And so I think, you know, and frankly, we can also make use of some of the like the component level technology advancements that are really being funded by the massive pools of money that are going into, you know, developing these autonomous cars and cell phones. So I really see it as a good thing in that, you know, we're broadening the applications in which LiDAR is used to the point where, you know, my partner's got a LiDAR in her pocket. It's pretty awesome.
Okay, thank you. Right, so so this is the end of sessions. You know, thank you so much, Andrew, for your times and presenting very comprehensive in, you know, presentations, teach us about LiDAR technology and a fundamental and the state of the art. Thank you so much. So
it's my pleasure. Thank you very much for having me.
Right. So Andrew's informations now you can see. So if you have questions, and please directly contact Andrew through the LinkedIn and emails, and they're shown here in his slide. Thank you so much. Okay. So this is the end of events, right? Thank you.